Hello, I'm Charlie on behalf of the co-authors to present our work. Our work is entitled with CodeMatcher, the code based on sequential semantics of important keywords. The code and the data related to our work can be found in the link to our replication package below. Well, it has been widely studied that code search is a key tool for software development, because searching and reusing existing code from large-scale repositories can improve software development productivity. For example, many developers search code from GitHub search engine as given below. When tapped in a natural language query, such as convert into a string, the search engine will return numerous irrelevant and useless code. Therefore, developers need a better code search engine to support their programming work. Generally, the GitHub search engine is an information retrieval-based model. It works in 4 steps in general. The information retrieval model first builds indexing for large-scale code methods from codebase, then perform code search according to the word matching degree between query and code in codebase. Then a reranking algorithm will be used to sort the searched code list and return the top key results to the users. The information retrieval beta model is favored by the industry due to the fast search response time, making the code search service always available. However, the search accuracy is bad. Users must frequently modify their keywords according to search results until obtaining a satisfactory result. In the recent years, deep learning technique has been successfully applied into the code search task to solve the semantic gap between querying natural language and the coding program language. Generally, the deep learning model works in 3 steps. A model gets query and codebase as input, embeds them into a shared high-dimensional vector space. By calculating the cosine similarity between query vector and the code vectors, the model can return the top key code vectors nearest to the query. Not like the keyword match, like an information retrieval-based model. The deep learning model learns the matching relationship between query and code by using big data with much less domain knowledge. Most importantly, the deep learning model can understand the irrelevant or noisy keywords by using the embedding technique. It can capture sequential relationship between words in query and code. However, the search response time is slow. This is a major reason that is not widely used in practice. After analyzing the pros and cons of 2 different types of code search models, one simple idea is to use the information retrieval-based model as a basic model to make sure the search response time, and add it with the feature of deep learning models to improve the code search accuracy. Following this idea, we will provide our model, CodeMatcher. To view the advantages of the deep learning and the information retrieval models, we first implement the indexing part of the information retrieval model. We obtained 41 plus 1,000 repos from GitHub, preprocessed the code by our tool generalizer, which can be found in the GitHub link. The tool extracts code from repos, pass the code into the abstract syntax tree, and captures the method name and method body. Note that we transformed the program tokens in method name and body into fully qualified name, such as transforming string to java.io.string, making the semantics more precise. Next, we built the index for codebase by using the Elasticsearch, a widely used text search engine. Also, we built vocabulary with frequency for codebase for further using. For querying, we collect 3 metadata to each keyword, including properties such as noun and verb, and frequency occurred in codebase, and self-defined importance, such as JDK noun is the most important one. Based on this metadata, we adjust the irrelevant words that are not noun, verb, adjective, etc., because they are not used for programming. For the noisy words that are not occurred in the codebase vocabulary, we generated synonyms for them by using the WordNet tool. Replaced the noisy word with the synonym most frequently occurred in the codebase. Finally, we stamped the words and built the search string. We designed an iterative fuzzy search, where a query is bound by a string of important keywords in query. And the wildcard form .star that connects important keywords is to make sure the sequential matching between words in query and code. With the optimized search query, we retrieved the matched code from Elasticsearch. If the total obtained code is less than 10, we remove the least important keyword in the search string and perform the search. The iterative fuzzy search goes again and again until we obtain enough candidate code and or no keywords left. After the search, we first remove the redundant result by comparing empty-defined hash values. Then we re-rank the candidate code based on how the keywords sequentially match the method name and method body, respectively. Note that we put the code with the more dedicated APIs to a higher rank. For example, for query convert an input string to a string with two passed code in codebase, we first collected metadata for each keyword, built a search string for Elasticsearch, and performed the iterative fuzzy search. After calculating the matching score between query and code, we ranked the candidates. We can see that the first code is ranked higher due to its higher sequential matching of the important keywords between query and code. More details can be found in our paper. To verify the effectiveness of the CodeMatcher, we compared it with three baselines, including one information retrieval model, CodeHow, and two deep learning models, DeepCS and UNIF. We trained these two deep learning models by using DeepCS training data. We built a large-scale codebase by themselves to extend the scale of DeepCS codebase and address its overlapping with training data. Finally, we obtained more than 16 million code methods as our codebase. We tested the models with 174 real-world queries, evaluated the performance by manual identification with four widely used metrics, including F-rank, success rate, precision, and MRR. We studied four research questions. We first studied the accuracy and the time efficiency of code search, analyzed the contribution of the CodeMatcher components, and compared CodeMatcher with GitHub and Google search engine. In terms of the search accuracy, our model CodeMatcher outperforms the business significantly. It implies that our future solution is reasonable and valuable. In terms of the search response time, our model needs no time-consuming training and deep learning models, and the search time is fast. These results suggest that the future solution is valuable, where one common server can reach industry-level response time for a very large-scale codebase. After performing sensitivity analysis for the key components of CodeMatcher, we can find that all components are necessarily required, where the sequential semantics of important keywords is a major contribution. By comparing CodeMatcher with two widely used online code search engines, we can find that CodeMatcher also significantly outperforms GitHub and Google search. Besides, CodeMatcher plus Google search can further improve the search accuracy. To analyze why CodeMatcher and baseline work or not for each query, we classified the results into 7 reasons. First, both the method name and the method body matched the semantics of a given query. Second, the method name matched but the method body not. Third, the method body matched but the method name not. Fourth, the method name is matched but the method body is useless. Fifth, method name is not matched and the method body is useless. Finally, the search code is repeated result. The results showed that CodeMatcher works mainly because they high sequential matching between query and the matching name. CodeHow works due to method body match, and the deep learning model works for both. The result also implies the fusion of these three types of models. In the code search, the conciseness and the completeness of code is also important because the ideal code needs includes no irrelevant line but address all the tasks expected in the query. Our experimental results showed that CodeMatcher significantly outperforms baselines in terms of conciseness and completeness. Also, we investigate why the deep learning models not work well on our codebase. We found that DeepCS and the UNIF works well when using DeepCS codebase, but they work bad on codebase due to the larger scale of codebase and the out of vocabulary issue. Tuning them with training data from our codebase can slightly improve the code search performance. Finally, we investigated why the word sequence is important. After analyzing all the queries, we found that the 79 queries showed the importance of word sequence. We classified them into 4 cases as shown in the table, such as the order of the multiple tasks, data conversion, conditional job, and the exchange of code word. But the baseline did not address that issue very well. In summary, for the code search task, we proposed to CodeMatcher to use the advantages of the information retrieval model and the deep learning models. Our experimental results showed that CodeMatcher significantly outperforms the 3 state-of-the-art. CodeMatcher can achieve industry-level response time for very large-scale codebase. CodeMatcher also outperforms the GitHub and the Google search engine for code search. Thank you.